So thank you for the invitation. Today we will, together with Bara and Vincent, present the results of our project we solved together. And the project tries to combine natural language processing methods and new database methods, which are called LingData, together to provide a better representation of legislation. And last year we had a similar presentation of the same project here at the same seminar. So the title today is the same as last year, but there is number 2. And we will present some new results we had during last year. I presented this last year, but for as a reminder, let me tell you something about the motivation we have for this project. So the basic motivation is that there's a lot of documents published on the internet by public bodies in Czech Republic. And most of these documents somehow link to legislation, to some act or a part or particular section of some act. And it's very hard today to find which documents of a given type link to some given act, particular act, or to some of its sections. What kinds of documents can refer to acts or in general to legislation? It's, for example, court decisions. If there is some decision of a court, it's a long text which somehow mentions different parts of different acts. Or we have some inspection authorities like Czech Inspection Authority, which has some results of its inspections. They are also published as documents, and they can link some parts of legislation. And there are other different public authorities or public bodies which, for example, provide some permissions to do something on the basis of some part of legislation, or each public institution has some agenda which is also given by legislation. So the description of their agenda is, again, it's a document which refers to acts. And today we don't have some common representation of all these documents and links between them. So it's very hard, for example, to say what inspections of some particular inspection authority, like Czech Inspection Authority, refers to some particular act. It's not possible to find today. So that's our first motivation. And the second motivation, which is maybe more interesting for you at your department, is that legal acts are documents which define concepts like accounting entity, for example, or something like this, and relationships between those concepts. And it's somehow described in the text. And as we noticed, people want to search for these concepts defined by the entities and for the relationships which are defined by the legislation between them. So, for example, if we take Accounting Act, we can see, if we read the document, if we read the text of the act, we can see that there is the concept of accounting entity. And the accounting entity has, for example, definition in the text. And it's very hard to find the definition because it's somewhere in the text. Or in the text, there are some obligations defined for the entity. Each accounting entity has a lot of obligations and also rights which are defined somewhere in the text. And it's very hard to find them, to represent them somehow, and to represent the relationships between the obligations, definitions, and the entity and the concept. So it's the second motivation. Try to develop a method which is able to extract the concepts and relationships between them and to represent them in a way which enables to search all information. So this is the motivation in general. And on the basis of this motivation, we have some objectives, what we want to achieve. So the first objective is to find a common data model, a language, machine interpretable language, which will enable us to represent all this information. And also to publish all this information, all the data on the web in some standard way, so that if there is some other public body which has information or data related to our data, so that the information can be linked together. And this is linked data. I'll explain it later in more detail. The second objective is should be a premise of this project, but it's not, because it's not available now today. It's that we need consolidated expressions of checked acts, because if you have an act, for example, accounting act, it has a lot of versions which we call expressions. Each version is called expression. And we have amendments. It's a document which somehow updates current version of the act and creates a new version. And these versions are called expressions. And we need all these expressions of checked acts to be able to do this linking. But in Czech Republic, it should be published by Czech government, but it's not, only partially. So, or you can buy it. There are companies which create those consolidated expressions instead of the government, but it's too expensive. So we tried. Our second objective was to reconstruct those expressions. It was quite hard, but we have something thanks to our students, one of our students. Third objective was to use machine learning methods for recognizing the references. It's related to the first slide. These are text documents, and they somehow refer to acts or their parts. And the references have no standardized format. They are written somehow. So we tried to use machine learning methods to recognize those references. This was done by Vincent last year, and I presented those results last year, so I'll skip this today. And the last objective, which we worked for last year, was to use NLP methods to extract the concepts and relationships between them from the texts of the consolidated expressions of checked acts. And this will be presented in more detail by Vincent today. So here is a big picture of our project, the necessary step we have to do. The green part is my part, the orange part is Bara, and the blue part is made by our students. So as I said, we have one student who worked on consolidated acts, and we have also a team of students who worked on some web application, developed web application on top of the data we produce in our project. So as you see, we have some components which gather data from the web. We gather data from the Code of Law, which is published by the Ministry of Interior. They publish PDF documents with the texts of acts and their amendments. We consume those data, and the student produces the consolidated versions. We also download from websites of particular courts their decisions. There are documents in PDF or other formats, and this is consumed by Vincent, who used machine learning methods to extract the references from the text to the legislation, and he also has a tool which he will present today, which extracts the concepts and relationships. And we take outputs of all these components and we present them in a common data model I will present today. And we also link the resulting data to other data sources, because at our department we don't work only with legislation, but also with other data sources from the Ministry of Finance or Ministry of Regional Development and so on. We combine all those data together. We link them together. And on top of it, on top of the data, we develop some applications. And as I said, there is another group of students who also develop some applications. Okay, so the first objective was to develop a common data model. As I said, the common data model is linked data model. It's a very simple data model, which is based on the same principles as the current web of documents we use today. It's based on. So if you think about the current web, it's a set of documents. Each document has its address, unique address, which also serves as a locator. So if you refer to this identifier of the website, you get the content of the website. And the content of the website is an HTML code which contains references to other documents. And these references, these links, form the web. And link data take the same principles and apply them to data instead of documents. So if you have an entity, you create an identifier which is uniform resource locator, which identifies your thing. And if someone looks up those URL, he gets the data about the thing or entity. So, for example, if you take a person, for example, me, I can create some URL, for example, the domain of our department / Martin Nechasky. And if someone looks up those, he gets some information about me, but not as an HTML website, but some data. And the data should be represented in RDF. RDF is a format. I'll not explain the details of the format today, but it's developed by W3 Consortium, which also develops the HTML standard, and it enables you to represent any data in a common data model. So RDF is the common data model we use. And it's also a database model, so if you store the data in RDF to a database, you can query them using Sparkle. So you can take any data, represent them in RDF. You don't have to specify the schema of the data. It's very simple and easy, and you can store it to a database which is able to store RDF data, and you can query the data using RDF. It's quite efficient. Currently, in our databases, we have something like 1 billion of triples. 1 billion of records, and we are able to query them quite efficiently. And what's also important, if someone looks up an URL of your entity, you provide the data about the entity, but also links to other related entities. I'll show you some examples. And these links are similar to links between web pages on the web. So they enable you to create a web of data, not web of documents, but web of data. Okay, so I can show you some examples. So we speak about legislation, and if we consider some act, for example, value added tax act, we have a representation of this act in link data, in RDF representation. So it means that this act has some identifier, which is URL, and if you access this URL, you get the data about the act in RDF representation. We can try to look up this URL. You can use the web browser, and here, sorry. So I use the URL and looked up the URL using my web browser, and here you see the representation of the act in our database. And RDF is a very simple data model which represents data as triples: subject, predicate, object. The subject is the act, predicates are the properties of the act, and objects are the values of those properties. For example, here is the title of the act, and there are 3 different titles. This is because we work with 3 different data sources. One is the code of law, another are the court decisions, and the last is information about acts from the website of Czech Parliament. And each of them gives some title to this act, and you can see all these 3 titles. 2 of them have the same title. In court decisions, the act is referred in this as this expression. And for example, as I will show later, here are references to court decisions, and here are sections of the act. And I chose section numbered 100, and it's only the section. And as I said, each act has different versions. So the value-added text act has different versions, and the versions are here. So you can see that there are a lot of versions of the act produced by our parliament. And this is some of the versions, which was valid in the year 2005. And here are its sections, but the concrete versions of those sections. So you can see that if I go to more, here I'm some section which has text, and it's a particular version of the text of the section 102/1. It's some section of the act. And those texts were produced by the student I spoke about at the beginning, who created the consolidated versions of the act. So for each act, we have all its versions and its expressions, their expressions. I have to say that the student did the work, but he is not successful in each case. He's successful in, I don't know, 80%, I think. 20% of his data are not correct. So this is the basic representation of the acts. And as you can see, what's important is that each act and each of its sections has an identifier, which is also a locator, which you can use to refer to the locator and get the data. And also each expression of the act and each expression of each of its sections has an identifier. And we can use this identifier to link it from other data sources. And this creates the web of data. Which means if you have some documents or data which refer to a particular act or its section or some of its expressions, you can use this address to link, or any other address to link that section or that given expression of that section. And you can link your data to our data and enrich our data with your data. And we publish our data on the web. If you publish your data on the web and use these these principles to link the data, then it means that we create a web of data, linked data web, which we can consider as a huge distributed database with a lot of different data sources linked together. And in our project, we try to show that this is a useful representation of legislation, because there are several sources of data about acts. There are different sources of data about court decisions. Each court is a source of its decisions, and each publishes its data on its website, and they are not linked together. And if they use these principles, they would be linked together, and you could download all the data and query them in a way we show in this project. And as I said, RDF is also a database model. And if you store the data to the database, you can use a query language which is called Sparkle, and you can query the data. So, for example, I'll not explain the syntax of the language. It's similar to SQL language, but this query requests for all sections of a particular act with this number. And if you analyze the syntax, you can see that there are some patterns which have some variables, and those patterns represent the triples in our data, and the database engine just puts concrete values to those variables and returns the values of the variables which matched those patterns in the database. So this is a variable which represents some section, which is part of this object, which is an identifier of the act we speak about. And it returns all sections, therefore. So I've result of the query here. This is the result, so it's a list of all sections of the act, not its expressions, not the versions of the act, just representations of the versions of the sections. Another query is it requests the number of consolidated versions of particular sections of that act. So for each section, it returns the number of updates of that section, and you can see how many times each particular section of that act was updated. So here is the result. So you can see that there are sections of that act which were updated 4 times in the history, 3 times, and so on. It's the number of changes in that particular act. Another example I just go through is, that's interesting, it's the query on 2 different data sources. One data source are the consolidated acts, and another data source is the source of current decisions. And as I said, Vincent last year developed a software which extracted the links between current decisions and acts, and we represented his result as linked data, and therefore we can put this query which returns for each section of the act we speak about the current decisions which refer to this act. So the result is here. So here you can see, go somewhere here. Here you can see that this is a current decision. I think it's a supreme current, and in the text of this decision, somewhere is linked to our act, and in particular, it's section number 16. And here you can see that all these current decisions refer, these 2 decisions refer to this section, for example, and so on. So our representation and the software of Vincent enable you to put queries like, give me all current decisions which refer to this particular part of the act, or give me all parts of all sections of acts which are referred by particular current decision, and so on. And this is quite useful, and this was the first goal of our project, and we successfully achieved it. Currently, each day, each morning, we download current decisions of the courts which publish their decisions. Not all courts in Czech Republic publish their decisions on their websites, but those which publish, we download court decisions from their websites and process them by our software, which contains the Vincent software, and the result are links between the decisions and Czech legislation acts and their parts. So it's updated each day. Okay. Let's skip this. Okay. Okay, so this was, let's say, the first part of our project, just to somehow represent the legislation and the court decisions and other kinds of documents and links between them, and to represent the structure of the Czech legislation, structure of acts, which means the sections, and represent them as linked data to be able to put the queries like the ones I showed you. And the second part of our project we solve during the last year, let's say, is to be able to extract concepts and relationships from the texts of the Czech acts and to represent them as linked data in the similar way I showed you, and to enable users to query not the structure of the legislation of the acts and links between documents and acts, but also to enable them to query the concepts defined by the legislation and relationships between them. And first, Vincent will present you his results because his software uses natural language processing methods to extract those concepts and relationships, and then I will show you how we represent them in linked data, as linked data, and how we can use this linked data representation for interesting queries.
So in the first part of my presentation, I would like to present the general architecture of our system, and then I will present our first use case, and this is extraction of definitions, obligations, and rights from the Czech legal text. According to the International Data Corporation, 90% of all available digital data are unstructured. This amount currently grows twice as fast as structured data. In many domains, large collection of unstructured documents form main sources of information. Their efficient browsing and querying present key aspects in many areas of human activities. Typical approaches of searching large collection of unstructured documents are full text search and metadata search. In general, both methods do not work with the semantics of documents in any way. Restructure deals with the semantics of documents through the knowledge base. We define the knowledge base as a set of objects and relations between them. Restructure exploits three queries over dependency trees to extract both entities and relations. The outputs are represented in the resource description framework, RDF, and we believe that RDF, in connection with the SPARQL query language, is highly suitable not only as a database or querying tool, but also in the interpretation of the document semantic. So we designed the restructure architecture to be general, domain, and language independent. The system consists of 4 components. It's a conversion component, NLP component, entity detection component, and relation extraction component. Conversion component converts various input formats into internal representation. It's XML documents. The component offers several simple methods for importing, for example, plain-text or PDF documents, but it is also ready for more sophisticated conversion, one we implemented during the work on legal domain. NLP component provides a linguistic analysis of input text. It consists of the well-known chain of tools like sentence segmentation, tokenization, morphological analysis, tagging, and syntactic parsing. The procedures fit the framework of Prague Dependency Tree Bank, and all are available in the Trix framework. Entity detection component detects entities in the dependency trees. Entities are stored in the database of entities, and we exploit the PML-TQ tool. We prefer querying dependency tree to matching. We prefer querying dependency trees to matching the text with regular expressions because it allows us to detect entities also in more complex structures. For example, the typical example is coordinations. Now you can see that the entity current tangible assets is detected in the text current tangible and intangible assets. Another advantage of this approach is one-to-one correspondence between tokens in the sentences and nodes in the dependency trees. Thanks to this principle, we can directly mark entities also in the original input text. Relation extraction components works with dependency trees, with highlighted entities, and detects relation between them. It exploits also PML-TQ tool, and queries are stored and described in database of queries. For illustration, assume that user would like to search for a list of obligations which accounting units have to do. On this slide, you can see how Restructure will extract this type of information from the sentence účetní jednotky, které vedou účetnictví ve zjednodušeném rozsahu, tvoří opravné položky a rezervy, pouze podle zvláštních právních předpisů. Thanks to the NLP component, we obtain the dependency free from this sentence, and thanks to the entity detection component, we highlight the entities in this tree. Namely, the entity detection component highlight the entity účetní jednotky, účetnictví ve zjednodušeném rozsahu, opravné položky, rezervy and zvláštních právních předpisů. The last assumption is that database of queries contains a proper tree query. In our case, the query consists of the predicate tvořit, and subject must be highlighted as an entity, and object could be any subtree with analytical function for object. A restructure returns two relations in the form as you can see in this table. The names of the columns follow the formalism of RDF. They do not have to be subject, predicate, and object in linguistic point of view. So, extraction of definitions, obligations, and rights is our first use case for our system, and we concentrate on documents published in collection of laws of the Czech Republic. The style of legal text is generally considered very difficult to read and understand. Legal texts are specialized text operating in legal settings. They should transmit legal norms to their recipients, and they need to be clear, explicit, and precise. However, simple sentences are very rare, and typically the sentences are very long and complex. Now I would like to present how we adapted our restructure components for the legal domain. The first is conversion component. Also, legal texts have strictly hierarchical structure. There is no official machine-readable source of them with their structure. We implemented a rule-based parser for conversion of the input plain text to the restructure internal XML documents. The conversion tools creates a hierarchical structure according to different types of numbering and specific label, for example, for sections, headings, or chapters. This is the result. The result XML documents represent the hierarchical structure of the input text in a machine-readable format. We can see that syntactic parsing is a key procedure employed in our NLP component. However, NLP procedures we have at our disposal for Czech are trained on newspaper text. It's data from Prague Dependency Tree Bank. Since legal text and newspaper text essentially differ in syntactic features, we think that special attention must be paid to the verification whether we can use the parser trained on newspaper text also for the legal text, or some modifications are needed. To address this issue, we created the corpus of Czech legal texts. The corpus consists of two legal documents, the Accounting Act and Decree on Double Entry Accounting for Undertakers. It contains more than 1,100 manually annotated dependency trees and more than 35,000 of tokens. The selection of these documents was motivated in the wider context of the INTLIB project. Before manual annotation, sentences were parsed automatically, and then a human expert, Zdenka Urešová, checked each tree and fixed the errors if needed. Unfortunately, the source documents contains many enumerations and lists. From the language point of view, this list presents long sentences, which should be represented as one large dependency tree with hundreds of tokens. And this makes the manual annotation really hard. For example, the typical problem was to move one node through the whole tree. Therefore, we developed a special strategy for manual annotation. Long sentences were split according to formal layout and annotated separately. We used special links to define dependency relations between nodes from different partial trees. In the end, automatic procedure merged partial annotations back into one big dependency tree. The whole pipeline is available on our website. Currently, we still work on the evaluation of available parsers. However, we already proposed several preprocessing steps which intuitively improve parser performance. The first one is sentence splitting. To avoid the parsing of sentences with high number of nodes, of tokens, we split long sentences which appears in list into several shorter sentences. Thanks to the syntactic form of these lists, we were able to develop an automatic procedure which creates grammatically correct sentences. This table shows the example. This is then in an input sentence, and these 4 sentences can be substituted for this one. Another method is recognization. It means that recognization reduces the number of nodes, and several tokens are joined back into one token. On this slide, you can see the tree parsed automatically with the standard tokenization for this sentence. And this is the output of the same parser, which when we join these references into one token. In this pilot study, we decided to use manually annotated entities in our corpus as a third version of database of entities. Entities in our corpus were manually annotated by accounting experts from the SysNet company. Here you can see the sample of manually annotated text. The process of putting entity into our database consists of 2 steps. Firstly, each unique entity was parsed, and secondly, an automatic procedure takes entity dependency tree and creates the tree query. To evaluate the performance of entity detection, we provide 2 experiments. Firstly, we identify entities in sentences from our corpus with gold standard dependency trees, and then we identify entities in the trees produced by automatic parser. The table presents the results. You can observe that the precision is quite low. This is caused by the high number of false positives. This means that restructure detects entities which were not annotated in gold standard data. During the manual error analysis, we investigated that almost in all of these cases, gold standard annotation is missing. The human annotators were not consistent in their annotation, and they did not annotate each occurrence of given entity. Another conclusion of these experiments is very positive. I mean that we observed that using automatic parser has very low influence on the performance of entity detection. Our preliminary hypothesis is that automatic parsers works well on entities which are often something like noun phrases. In our pilot study, we focused on 3 different types of relations. The first is definitions. It's sentences where entities are defined or explained. The typical example is náhradním ubytováním se rozumí byt o jedné místnosti nebo pokoj ve svobodárně a tak dále. Then we extracted obligations. It's sentences where entity is obligated to do something. For example, k návrhu je navrhovatel povinen připojit listiny, kterých se v návrhu dovolává. And in the end, we extracted rights. We defined rights as sentences where entity has rights to do something. For example, nabyvatel může uplatňovat nárok z odpovědnosti za vady u soudu jen tehdy a tak dále. The three queries for detecting these relations were designed manually. The query design was driven by a strategy to cover maximum relations with minimum queries. The process of creating a query consists of following steps. Three-query expert browsing through the dependency trees and try to observe typical syntactic constructions for given types of relations. Then he or she designs the query for the matching the most frequent construction. The query is immediately evaluated, and expert can browse through the matches, and if needed, he can redesign the tree query. And these steps could be these steps he can repeat until some termination conditional is satisfied. In our case, it was that 90% of all matches are correct. In this pilot study, we used the first document from our corpus, I mean the accounting act for our query development. And finally, we obtained 5 queries for definitions, 4 queries for rights, and 2 queries for obligations. The evaluation was realized on the second document from the corpus, is the decree on double entry accounting for undertakers. In this test document, we manually detected relations and compared them with the restructure output. The test document consists of more than 700 sentences and 21,000 of tokens, and we manually detected them more than 400 relations. This line represents the restructure output. In total, restructure achieved precision of 80% and recall of 63%. Our preliminary results are in line with already published work. Almost all related systems report precision higher than recall, and the numbers are also very similar. As an error analysis, we determined the type of error for each incorrectly detected relation. The common type of error was that there was incorrect dependency tree, missing or incorrect query, or missing or incorrect entity. We can see that the results are very positive because syntactic parsers could be adapted on legal domain, and missing queries could be defined when we relax the strategy to cover just the most frequent syntactic patterns. We also use restructure on bigger data set. We prepared a collection of 28 documents with accounting and taxes provisions, and restructure extract more than 2,000 relations from this data. In the end, I would like to present the most frequent queries for the definition. In this case, on the position of predicate, that must be lemma rozumět, and the verb rozumět se. Then the entity which is defined or explained must be in the 7th case, and definition or explanation itself must be in the 1st case. A typical sentence is náhradním ubytováním se rozumí byt. This is the most frequent pattern for the obligation. It consists of the verb být povinný. A subject must be an entity, and object subtree is the obligation itself. And in the end, rights consist of the subject, which must be an entity, predicate must be verb moci, and object subtree must be object and must start with the verb. Typical sentence is nabyvatel může uplatňovat something. Almost each restructure component could be improved. In the NLP component, we would like to do evaluation and improving of automatic parsing. We want to implement automatic procedure which will offer new entities as candidates into database of entities. And in the end, automatic procedure could create 3 queries for relations. So that's all for me, and Dr. Hladka tell you something more about environmental domain.
The data extraction using natural language processing techniques, and then its transformation into linked open data. This is the general idea that we apply in the project, and we address 2 domains. First, the legislative domain and the environmental domain. We have started to apply this approach on the legislative domain, and now we apply the pipeline of steps on the environmental domain. No, the other one. I'm sorry. As in the legislative domain, we focus on acts and on on core decisions, and in the environmental domain, we concentrate on so-called EIA documents. When anybody plans to build something or anything, he or she has to assess the impact of his or her project on the environment. And the EIA stands for Environmental Impact Assessment, and the project documentation has to include a document on this assessment. Yeah? And in the Czech Republic, there is an agency called CENIA that administers the information system EIA, and this is the system where the projects are being applied. So here you can see the screenshot of the web page of this system. So you can go through all the projects that are currently submitted, and you can follow the state or the states of the process of assessment and so on. To give you an example on the structure of the EIA document, I use the story of Amazon, namely its plan to build a distribution center in Brno, and I call it no, yes story, because very recently the Brno councillors say yes, so they agreed or they support to the building support the project of the building of this distribution center. And I'm not sure when exactly they said yes, but in May 9 in 2014, so it means last week, there was posted a new intention by a developer, CTP Invest, and here is the documentation, the DIA documentation for this project. So you can, so browsing it, we can see that it's a rather detailed document. It consists of 57 pages, number of sections, and the company Sysnet that we cooperate with this company in our project. So they specify what to extract from this documents, EIA documents. And right now we focus on the section they call it B12. It doesn't matter what was the title of the section, but we focus on extraction extraction of data on quantity. So we have a list, or we have a database of entities specified by some expert, and we extract data like data that concerns the size of something, space of something, and so on. So here are some examples in Czech, examples on extraction of region something, on the number of something, and so on. We use the scheme, or we apply the idea of an extractor, and the AI documents consist mostly of tables. We can see a very limited number of paragraphs with sentences. Mostly we observe tables, so that's the reason why we don't work with PML TQ tool. It means that the strategy of querying dependency trees. Instead of we use the regular expressions. Yeah? So here you can see in this scheme, that here in two components on entity detection and relation extraction, we apply regular expressions instead of querying using the PML-TQ. For both components with entity detection and relation extraction, we need experts. First, we need experts on the given domain to specify entities and what to extract from the data, and then we need experts either for querying database trees or formulating decision trees. Regular expressions. Sorry. So here, here is some example. Ivana Lukeshova, our PhD student, is implementing the system for mining the AI documents, and so probably she will speak about it in details next week. Here is just example, and just to provide you with an idea what kind of problems or what kind of buildings we are working with, or we are reading. So to conclude the part on natural language processing in this project, the very important, I would say the most important part is the evaluation. And there are a number of aspects we view the evaluation process, and we have to consider the points of view of developers and users. And so we develop a system for users. We have experience with evaluation against the gold standard data. So it means that there is some tree bank or some data, tree bank data, manually annotated data, and we evaluate our system or parsers against the data. So we have some experience, and on the other hand, there are users. We are developing the system for users, and they have some expectations. I'm not sure if we really do understand their expectations, or maybe they still don't know what to expect from our system. But we have to design the system so that our experience and their expectation finally meet. And when we submit the paper on the results that we achieved in this project, and if we submit it to the NLP conference, so we typically we read the comment that the scientific contribution is low, but on the other hand, designing the system of the given system, in some sense we make life easier in the sense of searching the huge amount of data. So that's there are a number of aspects that we have to take into that we have to consider. And then now we are going back to the link data representation of the data we extracted from text.
Okay, so in the last part of our presentation, I'll show you how we represent the outputs of Vincent and Bara and represent them in link data as RDF. As I said, or as Bara said, the big issue in our project is scientific contribution versus usability for our outputs, and how how to explain our consumers, who is a company SysNet we spoke about, how to explain them that our outputs are not and will not be never with perfect precision and recall, that there is always some level of mistakes and so on. And I explain them that even though we are not able to achieve perfect results, which they finally accepted, we are still able to make life easier for people who search through legislation or environmental documents and so on. So we explain them that today what the system provides, for example, the users who need to search in legislation, is full text search. And we told them that if we are able to identify some entities, we can say then that here at this place of the legislation probably is a definition of a given concept, of a given entity. And the definition probably is this text. Or we can say them, this is some obligation of that entity or concept. This is some right of that concept, and it's here in this text. And we explain them that it's not possible to extract something from the text and put the extracted information to users. It always has to be linked to the original text. And that's also the goal of our linked data representation. Here is some example. Here is again some sentence. It doesn't mind what does it mean for our English speakers. It's not important what does this sentence mean, but it's important that there is some subject, some entity or concept which has some obligation which is here. And what we want to do, Vincent and his software extracts this triple. What we do that is we extract this triple to a linked data representation, something like this, and we link these, we call them text chunks, parts of the text, to their meaning in linked data representation, some concepts which are represented in particular parts of the text. And we say that this concept has this obligation, and the obligation is here in the text, and the concept has an occurrence here in this text, and that the concept appears in some part of some act, and the obligation is in another part of the act, and the concept also appears in another part of the same act or in another part of another act, and so on. So we provide a map of those concepts and relationships like has obligation, has definition, and so on. And users who work with this data does not work only with this representation, linked data representation. They always work in the context of the text. So if they search for this concept, we show them that it's here in the text, and the concept probably has a definition which is some text, but the text is here, so you can read the whole context of the definition. Or that probably it has some obligations which are here in the text, and you can read the whole context in the text of that obligation. So that's the goal. It's not the goal to extract something from the text, represent it in some database format, and to build the application on top of the database representation. We always provide the links to the original text. So the user can read a text of the act. He can then, if he sees some concept, for example, he can click on the concept. We can show him the other parts of the text where the concept appears and where the definition probably is, where are its obligations and rights and so on. And he can, for example, go through this map of rights and obligations. He can get to some other concepts, and from here he can get back to the text and so on. So he can browse from the text to the concepts and from the concepts back to the text. And that's important. And this seems that it could be useful for the users. So currently we are in, the project is in the state that we have the first version of the extracted concepts and relationships. We have their linked data representation, and we gave this to the company, to the SysNet company, and it's their business to present this somehow to their users. It's not our business. We just explain them what they are able to do with the data, what they are able to do with the text linked to some extracted information what they can do with this, and it's on them to develop a, let's say, useful user interface which will enable to normal users to use the data. So in more detail how our representation looks like, I will start with this level, independently of the text. We receive from the software, from restructure, from the software of Vincent, we receive some extracted concepts and relationships between them, and we represent it in RDF and somehow. It's this part of the picture. And the structure of the represented information is looks as this picture shows. It's a simplified representation, but it explains what's important. Each extracted entity is represented as a concept. For example, as Vincent showed you an example of accounting unit, I think. It's a concept for us. It has different versions because the accounting unit is extracted from the accounting act. It has, I don't know, 20 versions in Czech legislation. And each version provides a different version of the concept of accounting unit. So it has also its versions. And we say that the concept is part of some act, and its versions are parts of particular versions of the accounting act. And we represent the definitions and obligations and rights. Obligations and rights are, again, concept with respect to their versions, and definition is some text, some literal text. So this is a simplified representation in RDF. I can show you an example. It's a concept of employer defined by some act in some particular version. So if we just a moment here. So here's link data representation. It means that this is a concept. This is a concept, employer, concept of employer, and the concept of employer was extracted from this act. The representation of the act is here because we have linked data, so we can browse through different entities. And yes, it's not very important, but what we have is that the concept of employer has different versions. Currently, we don't have processed all versions of the act. We have only the current version, which is valid, the last version of the act. So we have only last version of this concept. So the last version of the concept of employer. And it's here. So it was this representation. And you can see that we have its definition extracted from the text. It was extracted automatically by one of the queries provided by Vincent. And it has some obligations. There are no rules. No rights. No right was extracted from this concept, only obligations. And these are not objects. The obligations are these objects, which are referred to as obligations of the employer, are not the objects. These labels are not intended for end users. These are our internal labels. I have a query which enables us to extract those labels. So there is the result of the query. So this is the list of obligations extracted for the concept of employer from that particular act, its last version. Finally, in the end of the project, we will have all versions, all obligations of employer extracted from all versions of that act. And if the concept of employer appears in some other acts, we'll also have obligations extracted from those texts. But I have to say that if I extract the concept of employer from one act, and the concept of employer from another act, I don't know if they are the same concept, semantically equivalent concepts. They are different concepts for me. Those two concepts have two different identifiers, and I need a domain expert, some lawyer or some other expert, who says that those concepts are the same concept. And in that case, we use link data principles to link those two concepts together. But still, they will be two different concepts. But someone says that, some expert says that this concept is the same as this concept, and this will not be done by ourselves. It will be done, or it will have to be done by the system company, who are the experts. It will not be done by us. It's a manual work, this linking of different concepts which mean the same thing, because they're in different acts, but they are the same thing. But this cannot be decided automatically. And as I said, it's important that this is only information extracted from the text. It's important if a user of some future application will ask what are obligations of the concept of employer, we cannot show him only this. This is a relatively nice example, but I can show you a lot of examples which are not so nice, because the obligation is only a part of text. We think that it's an obligation, and it's extracted out of the full context which is given by the text. So we also have to be able to show where exactly this text appears in the text to enable the user to read the whole context. And for this, we also have another layer of our link data representation. It's here, and as I said, these are concepts or their versions, and this, let's say, semantic layer, and here, from here down is the linguistic layer, or yes, linguistic layer, and here we have text chunks. Text chunk means that it represents a particular appearance of some concept, and it has some dependency tree. We also represent the dependency tree in RDF, and it has some form, and this shouldn't be form but lemma. So we exactly know where this represents the place in the text where the concept appears. So we are able to show, this is only non-user-friendly representation made by Vincent, but it's very important for us, because here is the result, and here we can see that this text, in particular, in fact, is a text chunk, and here we can see the ID of the text chunk. So, for example, and the IDs are here. So, in the original text, we marked the occurrences of these text chunks. So, if a user asks for obligations of an employer, of the concept of employer, we can show him this, and if he's interested in more details, we'll link him to the original text. And also, it's fact that a given concept has more different definitions in the same act often. So the user will work with our applications in our application in a way that he will put the label of employer. We'll say that employer is a concept, and it has some definitions, and the definitions are somewhere in the text. We will show him where exactly they are. We'll show him that it has some obligations, and they are represented in the text somewhere. And he can read the text. If he sees another concept here, he doesn't understand, he can click on the concept, and we will show him, yes, it's a concept, and it has some other definitions, some other obligations, and so on. So the goal is not to just extract information and present this extracted information, but to show that even we don't have perfect precision in recall, users still can work with the information we are able to extract from the text. Okay, so it was a quick demonstration of how we represent the extracted concepts and relationships extracted from the text. And there are some next or future steps we have to do. Partly Vincent spoke about them. His work is related to improve the extraction on the base of the queries. But we also want to, on our side, we will develop some applications which will demonstrate to end users how they can use our data. And also, we work with other data, as I said, for example, the fines imposed by public bodies like Czech Trade Inspection Authority. They say there is a fine and it was imposed on the base of act number something, part something. We'll link those fines to those parts of acts. But thanks to Vincent, we will also be able to say that this part which is referred by that fine also defines some concept probably, or some obligation, or some right. And we'll try to show that it's useful for end users. Okay, so that was the conclusions.